Hi, so I want to show something that I've been talking about on the channel quite a bit, but I'm finally making a video about it. So let's say that L is a regular, context-free, decidable, recognizable, whatever you want language. And let's say that F is a finite language. So it's important that it's finite here. Then what I want to look at is both adding the strings of F into L. Let's just assume for sake of demonstration that F and L are disjoint. So let's say that the intersection is empty between them. But if it ends up not being empty, then this will still hold. So let's look at L union F and then see what happens. So what we can actually show, and I'm going to look at in particular when L is regular, but this generalizes to all the other classes. So what I want to show that L union F here is also regular. So if I add a finite number of strings to a regular language, you will still have a regular language. Well, this one's actually pretty easy to show because if F is finite, F is regular. And if L is regular, by assumption, then by closure under union, we get the regular language at the end. So that's pretty easy. But another thing that you can also show is, now let's suppose that we have a slightly different scenario where we have F is a subset of L and is finite. Then what we can show here is that if we take L and take away all of those finitely many strings, then what we can get is the same result. So this again will generalize to context-free, to decidable, to recognizable, all of those language classes. This will have the same property, whatever it is, as what L did. So even if L is finite, this will still hold. So how do you actually prove this? Well, let's look at L minus F. Well, that's the same thing as saying L intersection the complement of F. That's just a redefinition of what that means. Well, for 3 of the classes, they are closed under intersection totally. So if, for example, if L is regular, decidable, or recognizable, then F complement is going to be one of those 3, and these 3 language classes are closed under complement. So this automatically holds for here. The one that's slightly different is for context-free languages, where they're closed under intersection with regular languages. But since F is finite, F complement is regular, because if F is finite, F is regular by definition. And so therefore, regular languages are closed under complement, and so we get this automatically. So that this is context-free in that case. So that's actually pretty interesting in that no matter what language you have, whether it's infinite, finite, whatever properties it had, you can add a finite number of strings or take away a finite number of strings, and the language that you get from it will still have the same property that the original one did. Which is pretty interesting because that would imply that the jump between 2 different say a regular language and a non-regular language, they must be infinitely many strings different from each other. Because if it was only a finite number of strings different, let's say from the regular guy, then we can add a finite number of strings into it, and we just showed that the result is regular. And so therefore that would be a contradiction because we just assumed that the language was not regular. So regular and non-regular, context-free and non-context-free, they're all infinitely many strings apart from each other, which I think is pretty interesting. So hopefully that was interesting. Leave thoughts about finite languages into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.